had this talk ready, I thought, well, I should be talking about the alpha effect. I've been involved with it off and on for a long time, but the work I've done recently has not been directly involved with the alpha effect or mean field electrodynamics. So I'm telling you about what I've been doing just recently. This is work that I'm doing with Andrew Basson, who's now in Australia, who was an ex-student, Sergei Stavchenko. The problem is motivated by rotating convection in, say, the Earth or the planets. And there's a lot of interest now in the situation where you may have regions of unstable and stable regions. This possibility comes about from reasons Paul Roberts mentioned yesterday. You have both regular thermal convection, you have other types of compositional convection, and so these possibilities do arise, and people are doing models of planets in which they have stable regions and unstable regions. They're planetary dynamos, so that's the dynamo connection. The model we're looking at here is one for which you have an unstable region near the inner boundary, and what should I point with? You have, this is, say, your inner core. Here's your inner core of your planet. There's your outer boundary, and the unstable region is close to the inner boundary. So that's the basic model we're looking at. It's linear. It's all Mickey Mouse stuff. It's linear. It's a classical problem that's been looked at for many years, starting off. Paul Roberts made this famous with his early work, and then Fritz Busser followed it up, and he had his celebrated annulus, from which an awful lot of convection problems have been looked at. Now, what's the idea? Let me just, because we need to know what's going on, or if I start showing you what I've done, you won't have the first idea what I'm talking about. The basic idea is if you have an unstable region and rotating self-gravitating sphere or shell, that the leading order force balance, as Paul pointed out yesterday, is is Coriolis force and the pressure gradient. So under that basis you get geostrophic flow, and that geostrophic flow needs to be able to convect heat. And the way it does it is by being basically constant motion which is independent, largely independent of Z, but it's forced to be dependent on Z because it's got to meet the boundary conditions top and bottom. So those boundary conditions force the Z dependence on you, whether you like it or not, in order to convect heat out. And the way this works, it depends on how what problem you look at. If you look at the problem that Paul and Fritz looked at, where you have internal heating, then this column, you get a localized column of convection which occurs at mid-latitudes. Now, this column is, I say a column, it's actually lots of little cells. They're in terms of the Ekman number, they're e to the third in distance that way. They vary slowly along the axis, and there's a radial extent to these columns. Fortunately, to do the stability problem, you may not have to consider that radial structure. I say you may not have to. If it's a free layer, then you do. But if you look at the other problem where you have heating between the two boundaries, which was the situation in the previous talk, then the temperature gradients are so strong near the inner boundary that the convection is tied up against the tangent cylinder. It doesn't like to be inside the tangent cylinder. So the convection wants to be there if you have differential heating. Now the model we've actually chosen is one in which you have differential heating between the inner and outer boundary, so the natural arrangement is for it to want to convect on the tangent cylinder. The second thing we do to make a smooth, continually varying distribution of buoyancy, most of the models that have been looked at have a discontinuity. They say we've got this buoyancy in one region, and another buoyancy in another region. We've got a continuous variation of buoyancy. And so the way we affect this is by having the differential heating between the inside and the outside, but instead of the uniform distribution of heat sources, we turn them into heat sinks. And by this device, you can get the temperature gradient, which is unstable, close to the inner boundary, and as you go away from it, it becomes stable. This in itself suggests the problem of convection in a thin shell. People have looked at convection in a thin shell. The situation, again, the pictures from the previous talk showed this. The radial velocity is it's in this region here, and it's got this short longitudinal variation, and so you expect convection in this region. Now, what happens next? You've got all your parameters correct. You've got a large, very small Ekman number. The Ekman number's got to go to 0 first. You can then deal with a small, unstable region. So there's a second parameter. That's not going to be too small relative to that. And then you still have the columnar structure. You still have the columnar structure in this region. And the way you solve the problem is to just take an e to the im phi out for the longitudinal variation and an e to the I omega t for possible wave motion. And that's one other ingredient I must mention before I get going. You begin with this geostrophic balance, but, as I said, boundaries force vertical motions. This in turn produces things which resemble Rossby waves. Now, the nature of these sloping boundaries mean that those Rossby waves propagate progradely. They propagate in the same direction as the rotation. And there's also a tilt in the prograde direction as you go out. That's why I've drawn these things like that. We're not interested in this tilt in this talk. Okay, but we are interested in whether they're oscillating modes, whether they're travelling modes. These are things we're interested in.
What is epsilon?
Epsilon is the well, it would be, I think, if we've got it, I'll show it in a moment. I guess that distance is epsilon squared, I think, but that's epsilon squared, but that distance between there and there is epsilon. It's geometrical. I'll show you. Just wait, you'll see it. I said all that. You've seen these equations. One slight thing that you'll notice, the IO refers to that the inner and the outer rotation rates are obviously the same. Everything's non-dimensionalized on the inner boundary radius. This is non-conventional. Most people use the outer radius for obvious reasons. That's nearer what you can see. But since everything is virtually independent of the outer radius, it doesn't make any sense to do it that way around. So we've used the inner radius. So we're going to look at a linear convection problem. You've seen these equations before. The Q is how the heat is distributed in the fluid. So if you had the limit, and don't everybody say we can't have epsilon less than squared less than naught. Just think of epsilon squared as a number. If epsilon squared was -1, these two go to infinity, this number becomes 1, you get the internal heating limit. That's when you have uniform distribution of heat sources, and Q is 1. That's the classic problem. If you go to the other limit in which, golly, which way you've got to go? Epsilon goes to infinity, I guess. If you go to the other limit, epsilon squared goes to infinity, you lose those two terms. That goes to r to the -3, and you have an r to the -3 there, which gives you the differential heating. Okay, so those are the two limits, and I've been asked about the epsilon. The 1 plus epsilon squared to the half is the radius at which the density changes, the density gradient changes. And in fact, it looks all very cumbersome here, but this is organised so that the distance upwards to that. You've got to think of the convection. I should make one other thing clear. The convection is in a much smaller region than the ray. You're thinking of convection in a region like that. That in itself is thin compared to that. So the epsilon is that distance upwards.
Just to make sure that while your sink includes velocity, if velocity is equal to 0, you have no temperature sinks, right? Q times U dot R or what?
Well, that's U dot grad theta. U dot grad theta.
Okay.
But what? Why not unit vector?
Yes.
Why not unit vector? Vector is proportional to R, is it correct?
No, it is R, it's the radius. It is the actual radius vector. It's not a unit vector. Just remind you guys what's going on. So take out the exponential. The way you do this, you take the curl of the equation. that gives you one equation for the stream function. You have a, if you like, horizontal. In the plane perpendicular to the rotation vector, you have a stream function. W is the axial velocity. Take the curl, take the z component, you get one equation. Take the curl twice, take the z component, you get another, and there's the heat conduction equation. So you've reduced this to a very simple system. It's only second order and linear. I've scaled things. Slight mystery why it's epsilon E that seems to come out. Because epsilon E is a slightly strange combination of the lengths, but never mind, that's what seems to be the right one. You can construct the equations. This, if you like, is the d by d zeta is the stretch length in the z direction. And these terms correspond to the Coriolis force. In other words, if you only had the Coriolis force, you'd have d by dz of these things equal to naught. So these are the things that come from the Coriolis force. And the buoyancy stuff is coming from this Q, and everything's organised so that the Q starts off at 1 down here and goes to 0 there and becomes negative up there. So the Q is the thing that's driving things. And for Q, for zeta less than 1, you have something driving everything. And the way you set this up is basically, the aim is to do an asymptotic expansion in epsilon. So epsilon's a small quantity here, it appears small there. So the C is the thing that's driving everything. At lowest order, you don't have it there. And basically, I've eliminated the heat conduction equation, and basically, the buoyancy is coming in that term. So these rotating problems are very strange. It's the psi that's doing the convection, but it appears to be driving the W. It's very strange. Okay. Boundary conditions. Just W is equal to naught on the midplane. And, of course, the normal velocity ought to be 0 on the outer boundary, but it's remote. And so all we do, when we do the asymptotics at any rate, is demand that the solution goes to 0. Andrew Bassam did some numerical results using eta equals 0.35. This is a relic of a lot of geoconvection problems. Right. Andrew did some numerical integrations with those exact boundary conditions for various values of epsilon, as listed at the bottom. And the results depend very much on the Prandtl number. So for largest Prandtl number, the rate, remember these m's are stretched. That m is not the azimuthal wave number, there's a third factor involved. Likewise, the Rayleigh number is stretched, and the frequencies are stretched. However, what you see on this graph and the subsequent ones is the various values of epsilon. The largest ones are the ones, oh, I've got to be pointing at that, isn't it? Is the one at the bottom here. As you go up, and this is actually the asymptotic solution. The frequency, and you'll notice that's been scaled with epsilon to -1, so it's actually a small frequency order epsilon. That again, that's the largest Prandtl number. As the Prandtl number goes down, it approaches an asymptotic solution. And all these things I'm now going to show you are much the same. As you decrease Prandtl number to 1, what you know is the Rayleigh number for the larger epsilon seems to be going quite a long way away. The frequency is beginning to show something a little bit strange, because p equals 1 is a rather exceptional value, but the frequencies seem to be getting bigger within that scaling. Then if you go further, say p equals 0.65, and you do the numerics, you get curves like this at moderate epsilon. As you decrease epsilon, you go down until you appear to approach something like that. The frequency has now not been stretched with the epsilon, so this is the true frequency within the scale quantities. And on the left here, it approaches the value. On the right, these things are all going down to 0. So what's happening here is very much like what's happening in the previous one. As epsilon goes to 0, omega goes to 0. So those are the numerical results. You can press on, more of the same. Whoops. So what about the asymptotics? How do you do it? Basically, you do an expansion in epsilon. The lowest order problem for psi is essentially gives rise to a parabolic cylinder function equation. It's the sort of thing d2 by dz squared plus something which is driving it minus zeta squared which is killing it, especially large zeta. That's the sort of thing you get. So at lowest order, the psi would look like psi naught times eta minus beta zeta squared. So that's sort of like the the solution of the lowest order eigenvalue problem. The W there is, I guess, the derivative of that function. It's got a, or roughly speaking, it's got a beta there. First sight, you get some interesting information out of the lowest order problem, but you don't get everything you need. Everything you need only comes when you go to the next order. Right. The lowest order problem is very much like a classical problem of convection in a plane layer. It's very similar to the sorts of things we found in Chandler-Seeker's book on rotating convection. You can get two types of mode. You can get a steady mode, omega equals 0 mode, steady convection. And then for sufficiently small Prandtl number, less than 1 in fact, you can get oscillatory modes. And basically those oscillatory modes can either propagate to the left or to the right, or if you like prograde or retrograde. So there are two types of modes. So that's the lowest order theory. And that's, you were seeing that on those previous view graphs. So what happens? Zeroth order, you get three equations. You say three equations, you've got a second order system, you've got two unknowns, psi and w. Why have you got three equations? One of the unknowns is the beta. The beta which tells you how far the thing is going before it decays. So you actually have three equations. This equation would look more familiar if you drop the last beta squared and replace the first beta by the wave number in the axial direction, or the square of it. So if the axial wave number was L, then that first beta would be L squared. So it's not totally unrecognisable. That thing would look very much like the sort of thing you'd normally deal with. But in fact, it's slightly more complicated. This is the form you actually need. So you've got, what's happened? You've got two equations there, two complex equations for four unknowns. The R0, omega 0, real value of beta, and the imaginary value of part of beta. So it's all okay. When you analyse that dispersion relation, which is a lot of fun, despite its apparent simplicity, you get this sort of complicated structure. You get steady modes. And then you get these various oscillatory modes. So these are different values of Prandtl number. That's about 0.8, I think that's about 0.65. That one's drawn because the minimum there is the same as the minimum there. This one's drawn, it's 0.333 or something. That's because it joins on the minimum there. And then you go smaller and smaller and smaller. And of course, it's the minimum value you're interested in. That's the critical one. So the minimum value is there for a sufficiently large Prandtl number. When the Prandtl number's got to about 0.65, this minimum cuts in, and you then go off and the Rayleigh number drops. So there's a jump in the wave number from the steady mode to the unsteady mode is about 0.65. Those are frequency, I haven't got time for them. These are the betas, I haven't got time for them either. First order. When you go to the next order, it's a bit messy, but out comes this dispersion relation between omega 1 and R1. So basically the omega 1 and the R1 are assumed to be real, and this is a complex equation for those two unknowns. Now, from this equation, the steady mode, the omega equals 0, you can find out what omega 1 is in T and R1, so you find those corrections. Fast modes are somewhat more interesting because you get corrections. There's an R. Basically, the frequency of the correction is the same, depending on which mode you're looking at, whether it's the prograde or the retrograde one, but the R1s are different. And in fact, the R1 that is the smaller one is actually the R1 plus. This again is a long story, which I haven't got time for. So you're always going for the mode, the one which corresponds to the onset of convection is prograde. And the same with the omega 1 from the slow ones. They're always prograde, which is nice. That coincides with the sort of classical theories. I don't think we've got time for that one. Right, you can analyse. Yes, go back. Have I gone the wrong way? Yes. If you draw this diagram properly, there is a continuation of that curve. And what's happening here? These things are breaking away. Well, it breaks away at that point. And in actual fact, if you do the asymptotics, you can chase up what happens. The asymptotics tells you that these things sort of break off. So, for example, P equals 0.1, you're coming along the steady mode like that, it then breaks down on the oscillatory mode, the other one coming across there breaks down there. So you've got the two oscillatory modes. And the one that's lower is the one that's coming down from the right. It stays lower, except for some very small frontal numbers. And that's another, we haven't got time for that story, but basically that's the picture. They split. I don't think we can, I think we've got to summary time, haven't we? Summary. Right, let me just repeat basically the main points. When you do this asymptotics, the zeroth order resembles sort of classical convection, and so it's a bit as though you've got convection in a plane layer with the gravity inwards. There are some caveats to that. That's almost a bad example, because if it was really plain, then the convection could just be in columns and the rotation wouldn't affect anything. You've got to rule out that mode. So suppose you asked for the first mode which didn't do that, then it would be like the way I've described it. Let's see. So those are what Chandrasekhar would call the exchange of stability. Then you get overstability. They're the oscillatory ones. And they only occur for small p with plus or minus frequencies. When you go to first order, you've got to worry about curvature effects. Now, the curvature effects are due to the fact that here we haven't got a top boundary. This is remarkable. We don't have a top boundary. It's the fact that the density is varying with z. And these are the things that are really affecting things, because you don't have rigid boundaries top and bottom on this. He's just asking it to go to 0. But those, going to next order resolves these degeneracies. You can actually find the small frequency of the so-called steady mode, and the overstable mode split, and you get one of them gives you the one going prograde is the one that has the minimum Rayleigh number. There is one bit to this story which is, to me, very interesting. And that is that it didn't really dawn on me till the end. I thought, well, supposing you put rigid boundaries top and bottom there, and supposing you did this a bit like Husserl would have done with tilted boundaries, then you suddenly get a Rayleigh number, critical Rayleigh number, which is an order of magnitude smaller than the one we've got. I know ours looked small; it was going down to 0. But if you put rigid boundaries here, it's an order of magnitude p smaller. And this really worried me. I thought, have I got the wrong answer here? Has it all gone wrong? And I looked at it and looked at it, and everything's okay, and I tried other games to see whether this other mode would be the right one, and no, it didn't want to be driven. You can see it didn't want to be driven. So what's the point? The classical theories would all say, in the small Prandtl number limit, you have inertial waves. You have an inertial wave, and then you go to the next order to drive it. So you invoke buoyancy at order p smaller. So you bring the buoyancy force in the next order to drive it. These modes of convection are not like that at all. The buoyancy force has to be right in from the start, whether it's a small p mode or not. And I thought, well, why do we have to have it at the beginning? And then I thought, well, supposing you try and have inertial waves in this region. You can't maintain them. They would just want to propagate upwards. And so the rationale that I see is that if you can't, that mode doesn't exist, because you could have inertial type of modes here, but they'd be transitory. They propagate out into the region outside. So that type of mode of convection, which is sort of almost like folklore in the subject, doesn't exist in this problem. I think that's enough. Thank you.
A few questions. So, what is the role here of Rossby waves? Rossby waves doesn't play any role here? Or?
Well, it's certainly not the boundary that's making them propagate, that's for sure, because he doesn't feel it. But the buoyancy force, the fact that it's varying with height, it's also varying in direction, all these things, and the curvature, the fact you're in a cylinder, and so on, all these effects together seem to give you propagation. And what's curious is you're coming at it from a totally different limit. If you do something like what Fritz Husserl does, he says, well, he thinks of it in low Prandtl number limit to start with, and you can then think of Rossby waves. And then he says, well, when you have an order 1 Prandtl number, well, it was a bit like Rossby waves, but we bring the thermal diffusion in. It was a bit like Rossby waves. And these, they're not Rossby waves in the sense that you ask for the top boundary to give you a vertical velocity. They're not like that. But there are geometrical factors here that seem to give you the same effect.
On your last point about the inertial waves propagating away, do you think that means that this bifurcation is subcritical? That you could get behaviour, finite amplitude behaviour below the threshold that you were...
I don't think so. I don't think it's going that way. Well, I don't know. I have no idea. No.
Have you got density stratification in your calculation?
Yeah, that's the whole problem is density stratification. Yeah, it's stably stratified above and unstable below.
So density. No, my question may be a little bit another. What kind of condition you've got for velocity? Divergent sphere equals 0 or unelastic approximation?
Oh, it's Boost-Ness.
Divergent sphere equals 0.
Everything is Boost-Ness.
No, it's Boost-Ness too. Unelastic is Boost-Ness too.
No, but it's not unelastic. It's Boost-Ness.
No.
Either unelastic or Boost-Ness.
Yes, if I ask a question about this, I don't really understand why nothing can propagate within the tangent cylinder, because you're making the point that in some range your critical ray number dropped because of the boundary. Now the boundary gets closer to the pole, there's a shorter distance. So there must be some parameter range where the region inside the tangent cylinder convects more easily. You didn't look at this.
It's a long story. I mean, a lot of people have looked at this, and I don't think they... I remember Chris Jones, he was very pleased with the fact that he worked out that if you try to do it inside, the type of mode you get wouldn't want to convect heat very well.
They don't convect heat as well as the other ones. I know this because I looked at the axisymmetric modes a long time ago.
Yeah.
But it's still, the ray number is still proportional to the t to the 2/3. That's the top.
Oh yeah, I'm not saying, yeah.
So it's not a big gap looked at that way. It's not a big difference. You're not in another asymptotic range.
Are you saying that we should have looked for modes of convection problems there?
Yes, because you're saying that the convection was helped by the boundary when you put rigid boundaries at the top, and the distance that the convection cell has to spread out from the inner core to the surface is smaller when you're there. So in some sense it should convect more easily. In some parameter range anyway.
Well, I'm not sure.
The one you've drawn,
I can't answer the question. My gut feeling is it's not going to work better there. I mean, there's no evidence whatsoever that it will. I mean, there are convection models in thin shells, and they all show evidence of convection in that region down here. That's where all the numerical models show the convection for the thin shell models. I'm sorry, I haven't answered your question well. It's a tricky issue.
Any other questions? So thank you again, Andrew. And so the next speaker, soward+kapyla+, will talk about alpha effect and large-scale dynamos in convection simulations.
So, this is the project done with Marit and Axel during the last, say, 3 years. And this is mainly convection in Cartesian coordinates, in very simple systems. And what we are particularly interested in is large-scale dynamos, i.e. dynamos that produce magnetic fields whose length scale is larger than that of the convection itself. Okay, is this any better? Oh yeah.
Normal.
Now I can hear myself. Okay. So, this alpha effect in turbulent convection goes really back to Parker's cyclonic events in his 1955 paper. Here is a more recent picture which really shows the physical reality of the cyclonic event. So you have a field line, and then you have a convection cell which is coming up, and it's being rotated, and this brings you this loop of a poloidal field from an initially toroidal field. And if we consider then something more realistic, where we have lots of these guys, we can't really distinguish individual convection cells or anything like that, so we have to have some kind of statistical treatment. And a good example is found in, or if we apply the mean field theory in this case, and this is from the book of Fritz Krause and Karl-Heinz Rehler. So this is an example for for turbulent motions in a convective layer on a rotating body. And we see here that alpha effect has these different contributions, and the most important one probably is this one, which says that if we have a rotating inhomogeneous turbulence, then we should expect to find an alpha effect, and it's even noted here that this should be a quite natural phenomenon in convective layer on a rotating body. Okay, so how do we then compute these guys from simulations? And probably the first one to do so was Axel in this paper from already 1990. So here are Cartesian models of convection, upon which a imposed field is impressed, and then it's possible to get the electromotive force and then relate it to an alpha coefficient times the mean field. And here is an example for the horizontal alpha effect, and I seem to remember that this is from the south pole, so we have a negative alpha effect at the pole, and this is the top here, and this is the bottom of the layer. And this is something like a dynamo number here. This is the molecular diffusivity, and so we see that this is not a very large quantity in this simulation, but the Reynolds number is also fairly low. But this demonstrated that it's possible to compute the lambda effect from simulations with this method, and this actually agrees with the qualitative picture. I didn't show it here, that the alpha effect is not directly proportional to the negative of kinetic helicity, but at least qualitatively the trend is very similar. And going ahead in time for about 10 years, there is another paper with Mathieu Ossentreiber, and they were doing essentially the same thing, but in a slightly more turbulent case, and with a convection zone, or a model where there was also a convectively stable region below the convection zone. And what was important here was the dependence on rotation of the alpha effect. So what we see here, that there's two different alphas here given, and the upper one is the value in the stable layer, and the lower one is the value in the convection zone itself. This is again from the south pole, for reasons which are not entirely clear. Why do you have to do it on the south pole? And what we see here is that alpha is increasing as a function of rotation. And it's also important to study the latitudinal dependence of alpha. This is only from the pole, so it's only one latitude. And this was done in a subsequent paper. And what is found that alpha is decreasing when you go to the equator, and at the equator you have some residual value which is usually consistent with 0. And we also see that alpha is highly anisotropic, so the horizontal components have a very different distribution in comparison with the vertical component. But I will mostly be concentrating on the horizontal components here, because these are the, and especially the YY component, which corresponds to alpha phi phi, which is the important component in the alpha omega dynamos. And what was important in this paper was also the introduction of a new sort of method how to deal with gradients of the mean field that develop when you impose a large-scale homogeneous field on your simulation. It will not stay homogeneous, but it will generate gradients. And for our method to be valid, so that we can relate the electromotive force to alpha times the mean field, we should try to do it in from a state where there is no substantial gradients of the magnetic field, because then additional terms would appear in the expansion. And this is illustrated here by this equation, where the mean fields are homogeneous at times T0 plus I times T, and then this capital T here denotes the interval after which the field is reset back to 0. Okay, continuing in the same fashion, we then did some more work on this same subject and went to more rapid rotation, and we find that this is now only 2 points from the convection zone near the top and near the bottom, and we find that for slow-ish rotation the data is consistent with the cosine theta latitude profile, which is what you would expect from the simplest possible construct where you have the angle between gravity and rotation vector. But as you go to more rapid rotation, you see that the situation is different, so that especially alpha YY peaks around latitude 30 degrees from the equator. And the magnitudes here, these are now in strange cold units, but when you take the maximum value here and compare this with the turbulent velocity, is of the order of 10% or 20% in this case. So this seems, all of this seems fine, that we should have an alpha effect in our convection simulations, although this is not the full picture. There are series papers by David Hughes, Fausto Cataneo, and they are using essentially the same method to determine alpha, although I will show later what is the difference here and why this breaks down. And what they find is that when they increase the Rayleigh number or the Reynolds number of the simulations, then this cumulative average, time average of the electromotive force diminishes, and for the largest values it's very close to 0 here. So it seems to be that there was some kind of a debate whether the alpha effect actually exists, and certainly none of these simulations actually exhibited a large-scale dynamo. So this was basically the situation where we were in the beginning of 2008. We started to work again with convection, and thinking how is this possible that we don't see any large-scale dynamos. And one of the ingredients that is missing in all of these simulations I showed earlier is that there is no large-scale shear, which is thought to be very important in the solar dynamo. And what we did then is that we take essentially the same model, just a Cartesian box, where we have a convectively unstable layer and a stable layer below, and use the shearing box approximation. So there is a large-scale shear imposed on the convection. And Okay, then there's some dimensionless numbers that you should remember. Coriolis number, shear number, Reynolds number, and we have a very simple shear here, and then we always consider the rotation vector points to vertical direction. And what we find when we include this shear, we immediately find that there is a large-scale dynamo where the shear is sufficiently large. And we find this in the case where there is no rotation, and also in the case where there is rotation, and that for small values of the shear parameter, the growth rate of the dynamo is proportional to the shear rate. And
What is the density contrast?
the density contrast, okay, this is a fully compressible model, and in this case we had a moderate or small in our minds. It's about 30, I think, between the base of the overshoot layer to the top. So it's not extremely highly stratified here.
And what's the Rayleigh number?
The Rayleigh number is usually of the order of 10 to 6, or a few times 10 to 5. And okay, here are a couple of examples. This is a simulation without any rotation, but we have shear included, and this is a corresponding simulation with also rotation. And here we have Reynolds numbers, magnetic Reynolds numbers of the order of 30. And if we go back, we see that our Reynolds number is now based on the forcing wave number, or an estimate of that, which is just the depth of the convection zone, 2 pi divided by the depth of the convection zone. So our values of Rm are actually 2 pi times smaller than the canonical values used by many. And okay, similar results have then been also obtained by Hughes and Proctor for convection, and this work is also related to the non-helically forced shear dynamos by Tarek Youssef and collaborators, although I must point out here that even if we don't have rotation, we still have kinetic helicity in the system because of the stratification and also because of our impenetrable vertical boundaries. Okay, and then this is now one of our highest resolution runs. It will take a while before you see anything because this is now scaled with the values in the saturated state. What we find, this is now similarly as before, there's a horizontally averaged field. In the beginning you don't see really much, and then later on we get this formation of the large-scale magnetic field. And this is now for the highest Reynolds number that we have, which is about 250. And now you begin to see that in this simulation there is also a small-scale dynamo. So in the very beginning, the small-scale dynamo grows faster than the large-scale dynamo or the large-scale fields. And you see this very fibril structure of the magnetic field that was discussed yesterday. And only in the very late stages you see this very large-scale pattern emerging. And this is now different with different Reynolds numbers. If you have a small Reynolds number where the small-scale dynamo is suppressed, then we see this large-scale pattern from the very beginning of the simulations. And here I show we did something like half a dozen different Reynolds numbers, and we see that saturation level here is approximately the same. So now you begin to see formation of here's a blue field, which is negative streamwise magnetic field, and then you have a positive field here in the overshoot region. And this configuration does not show any oscillations of the magnetic field. And
So this one corresponds to which number?
this is the 251. So this took us more than a month to compute on 512 processors, so these are fairly intensive calculations. Okay, and okay, maybe I have time for this. So we also did in a subsequent paper, we studied the dependence on boundary conditions. We can either use the vertical field conditions where the field is vertical at the boundaries and the horizontal components vanish, or then we can use the perfect conductor condition, which defines the field lines within the domain. And the difference between these two is that, or one difference between these two is that these conditions allow magnetic helicity flux through the surface, whereas these don't. And what we find is that there is a difference of the critical magnetic Reynolds number at which the dynamo is excited. For the vertical field conditions, we find that it's close to 1, whereas it's about 5 times bigger for the perfect conductor case. And here we see this R to 1/2 scaling emerging at large Reynolds numbers, which is probably related to the small scale dynamo. And what we also then study is the final saturation strength of the mean field in these runs. And we see that for the vertical field, it doesn't vary too much, but it shows a weak decreasing trend as a function of the Reynolds number. Whereas for the perfect conductor, which doesn't allow helicity flux, there's a maximum and then a very steep decrease. But of course, our Reynolds numbers here are still fairly modest. If we compare to the Sun, we are 7 orders of magnitude behind. And it's very hard to produce any more points here because it would take half a year to get one more point. And we can't really argue that we have seen any asymptotic behavior here. Okay, then we would also very much like to understand why these dynamos are excited. And what we did next was to use the test field method, which was discussed yesterday by Matthias, and computed the turbulent transport coefficients for vertically varying mean magnetic fields, so that we have only four components of alpha and 4 components of eta. And I'm showing the results here for the case where we have shear and rotation both in the system. And we see that alpha effect is very anisotropic, and alpha xx has a different sign to alpha yy. And then what we did, we put these coefficients into a 1D mean field model and tried to, or then we measured the growth rates of the mean magnetic field in the mean field model. And we consider different cases here. So the solid line is where we have full alpha ij and eta ij tensors, and we see that it fits actually the simulation data, which is these crosses here, surprisingly well. So there is only one point which is significantly off from this. And but we also considered 2 other cases. We have the alpha shear dynamo, where we neglect the off-diagonal components of alpha and eta. We see that a dynamo is excited, but the growth rate is smaller. And we also considered the case where we have the all components of alpha are 0, so the dynamo is actually driven by the off-diagonal components of the eta tensor, which is the shear current effect, or the Nathan and Igor effect, and then the omega cross J dynamo, which is the Redler effect, of course. But in order to reproduce the simulation results, we indeed need all of these coefficients. And in the same study, we also looked at just rotating convection, which was done earlier in these imposed field studies. And what we found was that when we crank up the rotation, alpha keeps increasing and eta keeps decreasing. And that's the first time I saw these results. I thought, blimey, if we do a direct simulation with these in this parameter regime with rapid rotation, maybe we see a large-scale dynamo. So this is really based on a prediction from these test field results. Maybe if we do this direct simulation, we see a large-scale dynamo. And that's actually what happens. So this is slightly even more rapid rotation, but we do see the generation of fairly strong mean magnetic fields. Here this is the horizontal average again, and you see that the Bx and By both have a very similar magnitude, about 1/3 of the equipartition magnetic field strength. And okay, in this case, a horizontal average is fairly good to describe this mean field. And of course, like so many times before, then we realized later on that of course somebody else has done this before. This was a paper by Chris Jones and Paul Roberts, who had studied similar things in the geodynamo context already 10 years earlier. And what happens when we increase the system size? So the spatial structure of the magnetic field becomes more complicated. But if we look at the spectra, then this is the spectra from the kinematic stage when the field is weak. And we see that there is a peak at some intermediate scales, which is close to the peak of the velocity spectra. But when we go to the saturated regime, the magnetic field energy peaks at the largest possible scale. So this, to our minds at least, is a manifestation of an alpha square dynamo driven by convection. Okay, and then we come to the part which was kind of left open earlier, so the discrepancy between different determinations of alpha using the imposed field method. And the problem there is that if one just imposes the field and runs for a very long time, then you get these additional magnetic fields generated in your system. So your imposed field is no longer the full mean field. So then it's impossible no longer to use this sort of formalism where you have alpha times B equaling the electromotive force. But you need to have at least this sort of configuration where you also take into account the generated field, and not only that, but also the turbulent diffusivity. And this is what we did in this paper, where we compare just the electromotive force itself, which is the solid line, with two different descriptions where we have alpha determined from the imposed field method, which is given here, and eta determined with the test field method. And we do get a much better representation here. If, on the other hand, we would have used this sort of formalism, we would have got a very much smaller alpha than this one shown here. And then the correspondence here would be much worse. So what is important is to be very mindful of these gradients of magnetic field in order to get the correct value of alpha. And actually that was all I had. So we showed that you can get a large-scale dynamo in the presence of shear, and you need all the components of the alpha effects, the Rayner effect, and the shear current effect to explain the simulation results. And then if rotation is rapid enough, we can also get an alpha squared dynamo. And this is consistent and predicted by the test field results. And then you should use great care when using the imposed field method, or then you should really use the test field method instead, which doesn't suffer from these issues. And I still have some time, so I will show you the advertisement. We have 2 postdoc positions open in Helsinki, so if any of you is looking for a job or knows somebody who is looking for a job, please let us know. So it's work with myself and Marit on issues related to solar and stellar MHD modeling. So, thank you.
Thank you.
question about the, we have rotation, we have shear, and we have stratification, and also you have homogeneity of turbulence, which also contributes to. So have you tried to compare a role of stratification and homogeneity of turbulence? Just
that we haven't done in any systematic way.
Okay. Also, there are theoretical predictions for when you have rotation and shear. For example, if there is a slow rotation, which implies that cruise parameters is small, product of angular velocity by correlation time is small, then there are theoretical predictions that alpha effect is proportional to the omega multiplied by correlation length and square divided by stratification length divided by the homogeneity length of turbulence. The same for shear. If you have shear and shear artistic due to the shear multiplied by the correlation time is a small parameter, then it's possible to obtain alpha effect, which is shear multiplied by the correlation length squared divided by the stratification length.
Yes, I didn't. Yes, I didn't show the thing for the case with only shear. We of course did that similar to this. So we did measure also the alpha effect from runs with only shear, and there is indeed a contribution to alpha to that. I think it has a different sign than that of the rotation.
And what will be in the case of strong rotation? Alpha effect will be depressed by rotation or not?
Not at least in this range of parameters that we have. So we see that alpha is increasing. And eta is suppressed.
And this is without shear?
This is without shear.
When you increase the rotation rate just there, can you increase the Rayleigh number as well? Yes.
No. Rayleigh number is fixed.
So you're going to more and more laminar convection as you increase the Rayleigh number?
Yes. Yes. Yeah. Problem. I mean, ideally, you would like to increase the Rayleigh number so that the nonlinearity would be pretty much constant. But we didn't do it like that in this case.
My question about your calculation results. Is it similar to results of Shikachikin and Co?
Yes, I think I said it.
And first, and second, but nevertheless, you believe that, what is it, alpha effect or some kind of shear dynamo, maybe shear dynamo?
In the case without any rotation, but with shear.
But what kind of solution you find? Is it oscillatory dynamo?
No, it's non-oscillating.
So it's not alpha, it is not, definitely not alpha.
But also in the case where we have rotation, it's still usually non-oscillatory.
Why? It's normal solution should be oscillatory if it's alpha over the dynamo.
Depends on boundary conditions. I think for this one, when you run the mean field model, you also don't find oscillatory solution.
That I can't remember, but you're probably right. Yeah.
So I think that if you haven't oscillatory solution, it means that it's not alpha. On a shear dynamo, it is something shear dynamo without any alpha, because it should be accelerated.
Well, that's one would really have to study this systematically in order to make that conclusion.
What was your argument?
No, at least elemental study in without boundary conditions, in simple cases, plane geometry says that if you've got alpha effect and shear effect combination, it will be oscillatory dynamo.
No, but look for example, Karl-Heinz's calculations in a sphere.
But a sphere is not plates. It's not.
Okay, well then take the box, but then Karl-Heinz hasn't done it.
But it is
for the box. And for the box, the dynamo, an alpha-omega dynamo is stationary.
Maybe yes, but the question is what's the box? Is it box with curvature or not? It is plain box. Octagonal box. So it is not so.
So at least the results are very sensitive to boundary conditions. If you do a calculation for one set of boundary conditions with direct simulations, you reproduce exactly that case with the mean field calculation, and vice versa. And if you want something without boundary conditions, it's a different system that has also been done, of course. But then you can't do convection. Convection has boundaries.
And
Okay.
but rotation, just a moment. Vorticity, which is associated with shear, is it parallel to G or orthogonal? Parallel.
Yes.
Maybe time for 2 more questions.
So I completely agree with you in that in the turbulent electromotive force should be estimated in the combination of alpha and turbulent diffusivity. And I just would like to know, since you performed direct numerical simulation, you can estimate the coefficient alpha itself using, for example, helicity and also current helicity or something. Have you ever estimated using such?
Well, all of these calculations of alpha were done for the kinematic case.
Oh.
So there is a relation to kinetic helicity and not in the kinematic case.
I mean, your question should best be addressed in the case of force turbulence in the nonlinear regime, not in this convection, because with convection there's anisotropies and the simple relations that you have in mind don't apply. So in the case with force turbulence, we have actually done that, and that's in this 2008 Upj Letters paper, and there is a small departure between the alpha effect and what you would expect from a balance between kinetic helicity and current helicity. If you assume that both have the same pre-coefficient, which, however, according to theories by Nathan and Igor, is not actually true. There's minor discrepancies documented.
Yeah, you have not presented the mean field coefficients as k-dependent, as scale-dependent. So is it correct to infer that here the EMF and the mean field are essentially coupled by a local relationship?
No. No. So there is a dependence. We did it in the paper, but I didn't put this in the talk.
For gamma
yes, and also for alpha and eta, there is a dependence on K.
So was it essential to reproduce the simulation from the 1D model?
No, there we only used this, the results for K equals 1.
And K equals 0 or 1?
1.
1. And you could nevertheless reproduce it? Okay.
Fairly well, yes.
Okay, thank you. We turn to the next speaker. Thank you again for this presentation.
Okay, yeah. Thanks for the opportunity of being here in this very nice meeting. And I'm going to talk about buoyancy instability and dynamo action in simulations with thermal convection. But in this case, we are going to impose shear, but not in the same fashion that Petri just shown, but in the vertical direction. And this work is motivated in the conditions of the sun and on what are the real, or what is the physics behind the formation of sunspots. So here there are some properties of sunspots. They have a very, very strong magnetic field of kilogauss. The temperature is a bit less than the photosphere, is 3000 kelvins, and they are quite big. Here is the Earth compared with one of the sunspots. And going back to the outline of this talk, so I am going to show some of the basic work and some of the previous work made on magnetic buoyancy. Then I will show the numerical model that I am using here, and then I will go through my results, our results. This work is, I forgot to say, this is made in collaboration with soward+kapyla+. Well, sunspots usually don't appear alone, but they have almost always a pair. And there is a tilt between the pair of sunspots. Here it's possible to see even better in this magnetogram that there is a systematic tilt in the active regions. However, yesterday it was some discussion about this tilt, and it has been shown that in this paper, it was found by Kosovichev and Stenflo in 2008, that the tilt is probably not so evident at the time of emergence of sunspot, but it becomes, at later stage, it becomes more clear. And here is the tilt angle and the latitude, and here is the three different plots show different stage of evolution of the sunspot. So the tilt is more clear when at the later stage. Sunspots also have a periodicity. This is clear, and it is very well. Well, you can see it very well in the butterfly diagram. The sunspots appear in this belt very close to the solar equator. And so we believe that there is a dynamo governing the evolution of sunspots, but we still don't know. We are not sure what kind of dynamo is operating there. It could be an interface dynamo, flux transport dynamo, distributed dynamo, or maybe, who knows, an alpha square. This is all in the framework of alpha omega dynamos, but it could be also an alpha square dynamo. And where is the dynamo operating? It could be in the middle of the convection zone, where there is a pretty strong latitudinal shear, or at the Tacock line, or even at the near surface shear layer, where there is a negative shear in the rotation. So, one of the hypotheses for sunspot formation is magnetic buoyancy. So, magnetized plasma could become buoyant if, well, the plasma could become buoyant if there is magnetic field there, and if the magnetic pressure inside of the magnetized region, if the magnetized region is in equilibrium with the external region, in pressure equilibrium and also in thermal equilibrium, then this condition implies that the density inside of the magnetized region should become less and the magnetic field will rise. So it was developed a theory or a framework called the thin flux tube approximation, developed by Spruit in 81, and the instability condition is given by this. So it means that wherever a region is super adiabatic, then the isolated thin flux tube will become buoyant. And in this framework, several analyses were done, and for example here, considering a subadiabatic region which is supposed to, or which we believe exists below the convection zone, and maybe the Tacock line is also subadiabatic, then this diagram here shows for a region with this superadiabaticity or subadiabaticity in this case, that the magnetic field should be 10 to the 4 or 10 to the 5 Gauss to be unstable, and here the darker regions are for m equal 1 in the longitudinal modes, and this region is for m equal 2. And it's possible to predict the latitude of appearance of this flux tube and also the tilt that they will have at the photosphere. But when the magnetic field is not within the thin flux tubes framework, the condition is a bit different, and this condition was found by Newcomb. Maybe I need to go a bit faster now, and well, the natural step was to by two-dimensional numerical simulations, and it goes back to Fred Schussler, but this case here I am showing simulations by Yu-Hong Fan. And if there is a toroidal magnetic field or magnetic flux tube here, and it is rising because it's buoyant and unstable, it immediately forms these two vortex tubes, because the front of the buoyant region forms some vorticity, and the vorticity makes the flux tube to split. And this is a very well-known result. When the flux tube has some twist, so there is not only the toroidal component, but another component, the vertical component of the magnetic field is also there, then the conditions for emergence are much better.
Who twisted this rope?
Well, this is under debate, but could be the rotation or...
Lord?
Even, well, I will go back to this. But then, when the simulations are done in 3 dimensions, the things are better, because the bending of the field lines prevent the vorticity. And it's more easy to a longitudinal tube to rise. More simulations, previous simulations in 3 dimensions and in spherical geometry with an stratified atmosphere, but without any convection in this case. When the tubes appear at the surface, they form bipolar regions like this. However, in this case, the necessary twist for the magnetic flux tubes to show the same tilt angle between the active region at the surface needs to be requires a fine tuning. It's not so easy to have this. In the presence of convection, there are some attempts also. This in Cartesian geometry. Yu-Hong Fan has this simulation, and company. They allow the convection to develop, and then they impose a flux tube in the horizontal direction. And if the flux tube is, the strength of the magnetic field is larger than 3 times the equipartition value with the turbulent energy, with the kinetic energy of the turbulent motions, then the tube rises. And the rise is governed by the convection motions if the magnetic field strength is not strong enough. But if it is of around 10 times the equipartition magnetic field, then the tube of magnetic field rises, and it almost doesn't feel the effects of the turbulence there. The same result, or this result, had been confirmed by Luren Youth and Sasha Brun with the Ash code in spherical geometry. So this is the equatorial plane, and here is the tube, and there are 3 different cases for different values of the magnetic field strength. Well, there are some problems with the flux tube scenario. They require very strong magnetic field. They evolve in a turbulent medium. In these simulations here, the convection zone is not so stratified as the solar convection zone. There is not so huge stratification here. And we know that there is more than 20 pressure scale heights that expands the convection zone. So also the tubes require certain amount of twist, and the source of this twist is still not very well known. As Petri shown, the dynamo processes or dynamo simulation produce fields that are more that expands in the whole domain and not are concentrated in fibrillar structures. And also the magnetic field is pushed down by magnetic pumping, and buoyancy has not been observed. So a model that considers all the elements, all the ingredients that the convection zone has is still missing. And the reason for that is that it's very difficult to have everything in a single model. And even with the spherical geometry, the global simulations are still not able to reproduce any magnetic field behavior like we have in the sun. So we go to our model, and then what I am presenting here are results of simulations that include shear and turbulence, but there is not rotation here, so there is not helical turbulence, or there is not the coherent alpha effect. And this is a simulation by Youssef, and this is by Axel and collaborators, and what they found is that it's possible to have large-scale dynamo in time and with structures that are larger than the forcing scale. And then we use this idea to have a setup of a convective setup where we have convection and we impose a vertical shear given by this factor. We use the pencil code for performing these simulations. And what we have is, this is the basic setup. Here we have velocity in the positive direction, in the negative direction. Here the velocity is going in the positive direction, and we have a pretty good density stratification between the stable region and this region here is a cooling layer that we impose also. And we have around 8 pressure cascades in the domain, and maybe not that much, maybe only 6 in the turbulent region. And this is how the shear profile looks like. These are 3 different cases. One of them is a deeper tachocline or deeper shear layer, and the other one is a thicker. The Rayleigh number, a typical Rayleigh number for these simulations is 5 into 10 to the 6. In the brackets is the solar value. And the shear, this is our non-dimensional shear parameter, and this is for the solar case, and at the tachocline this is smaller than 2, with doing some estimations. And it's fair to say here that previous attempts have been done in this spirit, and this is a simulation by Tobias et al. In 2008, and there is convection and shear in this case, but in the Buzinski approximation. So in this case, it's not possible to observe or to get buoyancy instability. They reported that there is not a large component or a large scale component of the magnetic shear. And this is another attempt by Vasile and Brumel, 2008. And in this case, there is not convection, but there is the strong shear layer located in the middle of the domain, and there are fragmentation of this magnetic field layer, and occasionally these magnetic structures form here. But the results that we have is that we have a model with a magnetic Reynolds number. Well, these are our parameters. The prime number goes from 3 to 20. The magnetic prime number is around 1.6 or 1.5. And we go increasing the shear parameter by increasing the velocity, the shear velocity. And we obtain here that when we have a very strong parameter compared with the solar value, we are able to develop a dynamo.
Here stratification is fixed.
The stratification is fixed.
It's what stratification?
Yeah, I show you here that there is this is the density stratification. We made several runs by changing the depth of this shear region and also by changing the thickness. And here are shown some of the results. So for the shear layer located deeper down, we have a faster growth rate and the dynamo saturates at a very high value. But we also have cases with thicker tachoclines. And in this case, well, we are here in this set of simulations, we increase the thickness of the shear region, and we obtain still a dynamo, still a large scale dynamo. This is the fraction of mean magnetic field compared with the total field. So it's around 30% of the magnetic field is in large scale, and we obtain that for thicker tachoclines the growth rate decreases, but we have larger values of the mean magnetic field, which is somehow strange, isn't it? This is the case with a thicker tachocline, so it grows very, very slow, but finally it produces a very large scale magnetic field. We increase the resolution of the runs, we change the aspect ratio also, we increase the resolution of the runs, and when we increase the resolution we have dynamos that grows faster, so they are more efficient in this sense, but the final RMS magnetic field decrease its amplitude. Here in this plot are shown the distribution of, in dashed lines are the fluctuating component of the magnetic field, and in continuous line is the mean component, so the large scale component. This is for the deeper shear layer, so this is somehow explained because it's a very stable layer, so the magnetic field can stay here longer, and the magnetic field can grow easily. But it's kind of confusing, the case T04 and T04, this black line and the blue line, because in this case the shear region is located at the same position, but the shear factor from this to this decrease, and we have a larger magnetic field in the case with a larger shear region. So this is a bit confusing, but we then studied the results and what we found. So we went into the instability condition for buoyancy. This is a condition only for not longitudinal modes, it's for interchange modes only. And what we obtained is that in the cases with thinnest tachocline, the system, the thermal properties of the system change, and here the convection zone extends a bit deeper down, and the instability region is not only the convective region, but it also goes a bit deeper, and this is for the case with deeper tachoclines, which are the worst in this sense. The magnetic instability develops in the stable region very easily, but in the case of the thicker tachoclines, the system remains, the thermal conditions of the system remains almost unchanged, and the magnetic instability develops only in the convective zone. These results are for horizontal average. So we are not saying here that in this case we don't have buoyancy. There are events of buoyancy in times where the magnetic field is very strong, like is shown here. This is the magnetic field, and this is how the magnetic field organizes in the midplane here, where the shear is located. So there are very elongated structures, and then they occasionally become buoyant when they have field strength larger compared to the equipartition value at the same radial position. So let me show you how the evolution of this looks like. So there is convection, and there are magnetic fields that are becoming buoyant at some point. This is in the saturated stage, and sometimes they go pretty up. We can see here that there is a very large scale magnetic field in the Y direction. When the magnetic field is quite strong, the convection cells may become larger. And if we wait a bit more, we will see some situations. For example, here there is a larger convection cell, and here is an enormous field going up, but then they expand. They are not so coherent like here, but they expand and form these mushroom-shaped structures. For example, I think here or close now, yeah. The magnetic field rises up to the surface, and they modify the convective structure and form these elongated convection cells in the horizontal direction. This is how it looks like when we check for the magnetic field lines. So there are magnetic field lines covering all the horizontal domain. Here is the base of the convection zone where the magnetic fields with large amplitudes are generated. This is another case. Here is shown the magnetic energy, and here the magnetic field is rising only in one expanded convection cell. And here I can show you how it looks like. I hope the contrast is okay. So here you can see the magnetic field lines, and here it's possible to see how the lines rise when there is an upward flow, and in the middle here there is a strong down flow that push the magnetic field lines downward. This is for the a case with a better resolution. And here are the magnetic structures. Only the positive values of magnetic field are shown here. The negative magnetic fields, because they form of both polarities, are not distinguished easily. And in this case, there are 1, 2, 3, maybe 4 magnetic stripes in this direction, and then they rise. And then they form these structures here, or this structure here, which is shown in the magnetic field lines here. And if we see from frontal view like this, we see that this stripe, the field lines of this stripe, are reconnecting with this other one and forming this loop here in the upper region. This is the time evolution. The loop expands. And afterwards, there is another loop forming between this stripe and this central one here. Okay, so we can also compute the buoyant velocity, and for that we use horizontal average, and then we have these contours of magnetic field rising up, and then we compute we made an estimation of this, and this results to be smaller than the URMS velocity. This is not compatible with the results of magnetic flux tubes emergence. It's pretty small velocity. But we have to think here, or we have to remember that the URMS velocity is affected by the imposed shear. We have also studied the back reaction that the magnetic field has on the shear profile, or of the imposed shear profile. And what we have is that there is this is the residual vertical velocity. So it's the total velocity minus the mean value of it. And then we have that we have always an excess of this quantity above the shear region in the dashed line. But when the magnetic field increases or has peaks, showing here with the white line, it changes. So there is an excess, and then we have a decrease. And this situation is observed in all the simulations whenever we have peaks on the magnetic field. And this is, of course, not. It's only reminiscent of these bands of larger and lower sonar flows obtained by heliosismology. We also wanted to explore what is the kind of dynamo operating in this system, and we use the test field method for that. The components of alpha are basically zero in mean. They have a large variance, but in average are zero. So this gives us the possibility of an incoherent alpha effect or the shear current dynamo. Here is the turbulent diffusivity, and here is the turbulent pumping. The dashed line is the residual one. The real pumping is this continuous line here, so it's negative. And the amplitude of the pumping velocity is smaller also than the URMS velocity, but it's also smaller than the rising velocity of the magnetic field. So in summary, we have dynamo action with turbulent convection and a strong shear. Probably it's the incoherent alpha effect, probably it's the shear current effect. The magnetic field forms large-scale magnetic structures elongated in the direction of the shear. Models more stable to buoyancy develop a large-scale magnetic field easily. Local values of the magnetic field can be up to 6 times the equipartition value, and in this case, the magnetic is when the magnetic field rises up to the surface and modifies the convection pattern. Buoyancy velocity. Oh, what is? Magnetic buoyancy is very common, but when the tubes or with these structures rise, they expand and they usually break. The resulting buoyancy velocities are larger than the pumping velocities. In this case, the buoyancy is winning. But it's quite difficult to extrapolate this situation to the sun, so the physical origin of sunspots is still to be verified. Okay, thank you very much, and my congratulations to Karl-Heinz.
Any questions?
Shear flows tend to stabilize magnetic buoyancy instabilities and make them more two-dimensional, and that means that you're very sensitive to the aspect ratio of your box, and also it's sensitive to the ratio of the diffusivities that you find. Did you vary any of these parameters?
Yes, you're right. So here are simulations with two different aspect ratios, and if we change the dimension of the box in the not in the same direction of the shear, but in the perpendicular direction, in the x direction, I mean, the system behaves the same than previously. But if we increase the box size in the same direction of the shear, then the dynamo is less efficient. It's less efficient. Yeah. the mean value decreases, and also the growth rate and the RMS.
What about the ratio of the diffusivities?
You mean heat diffusivity and magnetic diffusivity. We have also tried this because if you see here we have different prime numbers, but there is not any important effect that we can distinguish here. Maybe at smaller prime numbers the growth rate is smaller, so it means larger thermal diffusivity. Yeah, but for the magnetic field there is almost nothing, apparently nothing outside.
Here in the system you have strong stratification and you have vertical shear. And maybe this is the reason why there is no mean alpha effect here. Yes.
And there is no rotation.
Yeah. Yes, but shear with stratification can produce.
But with the vertical...
Yeah, but for vertical shear, okay.
Another question?
What about the surface appearance of the magnetic field? Do you see things like bipolar regions?
No, because, well, if I plot the magnetic field lines, it's something like this that I shown. Like this. But if I plot only the vertical field component, then I have very strong magnetic fields in the downward regions. And which is a small scale, but it's even stronger than the mean magnetic field. So it's yes, no, not in. It can be no, not exactly bipolar. Yeah, I made that, but there is not something clear. You mean because of these field lines here?
And here you look into the depth, right?
Yeah, this is at the surface. It's close to the surface. This.
Not a surface.
No, it's just going down the cooling region that we use. Yeah, but we haven't seen any in a vertical slice of the B set component any evident or big bipolar region.
Okay, so thank you, Gustavo, again. And thank you to all the speakers. Now we go for lunch.